All right. So what we have here for your warm-up is just a reminder and a refresher. So go ahead and put your SFL packet away and take out your notes that you had, because on the back of each note page was your homework. And I want you to start on this side of the warm-up, and I want you to go ahead and draw color. If you need colored pencils, there should be some in your baskets. If there's not, I have my colored pencils over here for you to help yourself too. But I want you and your groups to talk about major, minor arcs, semicircles, the difference between the measure and the length of arc, XZ, and the area of that sector. And then move on and talk about tangents and chords. Say hello to your group mates and let's get going. All right, so when we start looking at major and minor arcs, having a colored pencil helps ridiculously so. When I'm talking about a minor arc, I can talk about arc XZ, and a major arc, I can talk about arc XWZ. And I want you to notice for each of these arcs, they both stop and start with X and Z. So how do you know which way to go around the circle? Your minor arc has a measure that's always what? Lower than 180 degrees. So when I'm talking about this minor arc, XZ, I'm talking about this guy right here. If I'm talking about my major arc, what do I know about that?
It's greater than 180.
Is going to be greater than 180. So we can go ahead and talk about this part of the circle, and this W tells me where it passes through. Notice they both stop and start with X and Z, but it goes my other way around the circle. So arc XWZ is going to be that major arc. All right, anytime that I have a semicircle, it's created by a chord with endpoints on the circle that goes through the center. What is that called?
Diameter.
That is a diameter, and that is when the measure is equal to 180 degrees. Well, doesn't that make sense that your angle, your linear pairs, are 180 degrees for your straight angle? And then doesn't that make sense that your semicircle also has a measure of 180 degrees? All right, we need to do some algebra to help us find the measure of Z, of arc, ZX. Hey, tell me, what's the difference between the measure of the arc and the length of the arc? Go ahead, Mason.
Isn't length of the arc like the outside on the perimeter, while the angle is just how wide open it is?
Yeah, perfect. So here, this angle measure is going to be the same measure as this arc measure. So this central angle with its vertex on the center is going to have the same arc measure, the same degree measure as this arc. When we're talking about the length, we're talking about if I were to put a piece of string around it, how long would that piece of string be? Before we can do that, we need to do some math. Give me an equation that's going to help me figure out what these angle measures are. What do we do with them? Go ahead, Serena.
3a plus 24 equals 180.
All right, so 2a plus 24 plus that a is equal to 180, and Serena went ahead and combined these like terms. That's where she got that 3, if you're curious. 3a plus 24 is 180. 3a is equal to, what's that, 156? So then a is equal to, what's that, 52? Do you know the divisibility clue? If the digits of a number add up to a number that 3 evenly goes into, then 3 goes into that number. So see how 1 plus 5 plus 6 is 12? 3 goes into 12. So I know that that's going to divide out evenly. Anybody ever hear that trick before?
Wow.
Every single number that 3 evenly goes into, if you add the digits, 8 plus 1, 9, right? 27, 2 plus 9, or 2 plus 7 is 9, right? If it adds to a number, the 3 goes into, then the 3 will go into that number. All right. Now I know A, now what? So A is 52 degrees.
You have to put it into the.
Yeah. So you've got a choice here. You can put 52 in here and then subtract 52 from 180. What's that, 128? Or you can do 2 times 52 plus 24. So 2 times 52 is 104. 104 plus 20 is 128. So because this angle, this central angle, has a measure of 128 degrees, so does this pink arc, which is minor arc XZ. We good? All right, when it's time to find the length, ask yourself, am I a proportion person where I talk about my part to my whole? So I have 128 out of the 360 degrees, and that's going to be equal to my length around my arc compared to my whole. My circumference is equal to 2 pi r or pi d. Since I have an r here, I'll go ahead and I'll use this formula, which is 2 times pi times, and that r has a radius value of 5. So if you're a proportion person, you'll go ahead and you'll solve cross products. If you're an equation person, you said, hey, that length of that arc is equal to this fraction of this whole. If you solved your proportion, you got that same equation. So when I go to do my multiplying, I know that 128 times 2 times pi, 128 times 2 times pi times 5, divided by 360, 11.17. And I do my little squiggly equal signs to let everybody know I estimated. It didn't come out even. Raise your hand if you think in terms of proportions and you write proportions, part to whole. Raise your hand if you think in terms of equations, that you know that's a fraction of that. So whatever you do, talk yourself through finding the area and you mark it, set, go. If you need to see how I do my calculator, I go ahead and I multiply my numerators. And then I always press enter and then divide everything by that denominator. If you're pressing the right buttons in the wrong order, your calculator knows the order of operations, and you got to be careful that you're asking it to do what you want it to do. That's why you need to be doing these problems with me. You need to be pressing the buttons. You need to be looking down and like, yep, we matched. I'm good to go. With practice comes speed and accuracy. Sitting by and passively learning math will get you a nice, mediocre, most likely disappointing grade. Let's avoid that. Questions on arcs, sectors, minor arcs, major arcs, semicircles, length of a arc, and area of a sector. Anybody want to talk about anything? Go.
On the question before, wouldn't it be 11.35 units split?
11.35?
Yeah.
I get 11.3.
When you round up, the 6 would round to the 4.
Yeah, but I only go out one place further. So see how, like, so here I am at 11. Here's my tenths. Here's my hundredths. I go one more out. See it? So if that were a 4, 3, 2, or 1, I leave it be. A 5, 6, 7, 8, or 9, that's when I round up. It's tempting because this 6 makes this 4 round, and you're like, oh, this 4 makes this 4 round. Oh, next thing you know, you're rounding everything up. Alright, good question, Sally. Thanks for asking. Alright, ready? Next step. We learned two big ideas about tangents and chords and arcs. I'd like you to mark up the diagrams and tell me what's true. Fill in the blanks. You mark it, say go. Alright, check it out. When I have the center of a circle Q and I want to get to the outside of the circle and I'm measuring the distance, I'm going to do it in a perpendicular line. That's how we were taught that we measure distance. That is the straightest, shortest distance. Well, that's going to hit right at that point of tangency. So my radius and my tangent line will always be perpendicular at that point of tangency. And you got to be a thinker. You got to be smart because where there's right angles, there's Pythagoras. So you got to get ready for a whole new slew of right angle math coming at you. All those right triangles, the sine, cosine, tangent. Think about every single thing we've done so far with a right angle. It's coming back because every time that a radius is drawn to a point of tangency, you have yourself a right angle. So be prepared. This next one, through hypotenuse leg congruence in CPCTC, we can see that these two segments from an external point of intersection are going to be congruent because they're the long legs of right triangles that have short legs that are radii and a reflexive hypotenuse that they share. So if you see those congruent triangles, then you don't forget that rule. Questions? Make sure your pictures match mine. Make sure your diagrams clearly help you remember each of these rules. You have a quiz next class on this stuff. So you're going to want to keep it in the front of your brain. Are we good? All right, on the other side of this, I've got two identical pictures to help us with two different stories about chords. And then this diagram should help you remember saving me from that tragic, terrifying avalanche. Thank goodness for geometry. Talk to your neighbors. Go.
It's a 2 out of 3 features.
All right, chords are congruent if what am I drawing? What big idea am I drawing? Chords are congruent if what does this picture show? They are equidistant from the center. All right, see if you can get this next picture. Two chords are congruent if what?
The sectors that they're in are congruent.
All right, so they're definitely in sectors. But we talk about what are these angles called?
There are the interior representative.
We have central angles. We have the related arc. And then we have the chord. If all of these are congruent within a circle or congruent circles, So my central angles open up a conversation about my related arcs, and my related arcs open up a conversation about my chords. So we don't really care about the in the same circle when we're talking about degrees, but as soon as we jump to a linear length for my chords, that matters. So two chords are congruent if they are equidistant from the center. Just imagine this chord shrinking down or expanding out. If it's a chord, its endpoints have to be on the circle, and chords that are the same distance from the center are guaranteed to be the same length. All right, talk to me about saving me from an avalanche. Which of the three features are we talking about? Call them out. A bisected chord. Tell me more. Perpendicular relationship. One more. And a diameter. A diameter is a chord that goes through the center of the circle. If something is bisected, it's guaranteed to be cut in half. And if it's bisected at the perpendicular angle, then the picture looks something like that. And this is where we have to realize that if I have any two is going to give the third. So any two of those shapes is going to give the third. Got it? Yeah? Okay. All right, so let's talk about this. Finding the measure of each arc, easy, not a problem. Just filling in what we're missing. Any problems with A, B, or C you want to talk about? I want to talk about 2 because guess what? You can't conclude anything about 2. What can you conclude about those arcs? A big fat nothing. So think about it. If I have a circle and I have a diameter and I have a radius and another radius, what's to guarantee that this triangle has bisected pieces or a right angle? Because I can draw this diameter and I can draw these chords that represent my radius any way that I want. So when I go to connect them and make a triangle, whether my triangle shifts left or right, it doesn't guarantee. Go ahead.
If it showed us that the triangle being bisected had a right angle, then would they be congruent?
Yes, if I had one more piece of information. So here I've got these are isosceles, okay. I've got these are isosceles. I've got these base angles, okay. I've got these base angles. But other than that, all I have is a diameter. And I know that this diameter intersects this chord, but nobody used the B word. Nobody said bisects. And nobody said it was perpendicular. If they had just given me one of those 2 pieces of information, I could have gotten the other 2. No such luck. So what can you conclude about arcs DC and arcs BC? The only thing I can say is that the measure of arc DC plus the measure of arc BC is going to be equal to the measure of arc DB. That's all I got. So if you want to add the pink and orange together, we can add that up. But guess what? I can't make any congruent statements. I can't talk about any bisects or angles.
So whenever we don't know if an angle is minor or major, do you always go with minor or just by figure?
So anytime that the arc is less than 180 degrees, you can get away with writing it as just dB, because this is smaller than 180 degrees. If I wanted you to go around the circle, I would have had to put an A in there. Now, if I wanted to be super careful, I could have said, okay, DCB, right? But if it's just two letters, it's guaranteed to be the minor arc. All right, let's talk about some circles that we can solve. When we look at KM, I do have it perpendicular. I do have it bisected, so I can set these two equal to each other and solve. Let's take a look at 4. I do have a diameter. It's just a little piece of one, but that definitely goes through the circle, and it is a right angle, so I know it's bisected. And then I can use Pythagoras to solve. For this one, A is just 1/2 of this. I see it's a diameter. I see it's perpendicular. I'm going to go ahead and double A's value. And I want to make sure that I double it. I left that off of this key. So 12.69 doubled is 25.38. This one's kind of funky because yes, I have a diameter and yes, I have a perpendicular, but you all know that you have a triangle because all you see is this X. So this radius is the same measure all the way around. So this 4.2 is the same as X. So I draw the radius. And I know that this 10 splits into 5 and 5 because it's bisected. So now I have Pythagoras. Go ahead.
Using the first one as an example, how do you know that, as an A, how do you know that just because there's a right angle that it's bisected? This wouldn't it be just a
Because it's a, remember if I have 2, I've got the third. Do you see the diameter? Do you see the perpendicular? There's your 2. So now I know it's bisected. See here, I see the diameter, I see the perpendicular, I know it's bisected. Same thing here, diameter, perpendicular, I know it's bisected. Are we good? All right, let's flip over, talk about the back. So these tangent relationships we have, hey, how did you do with multiplying your binomial? Did you FOIL, first, outer, and last? Yep. And that's Pythagoras to solve because my radius makes a right angle with my point and tangency. All right, let's talk about this one. External point of intersection. These two tangents are going to have the same value. We solve for x. And number 3, I don't know why we called it circle D. It's circle C. Hey, if you're taking the Quizzer test and you're not sure whether a numerical value represents the radius or the diameter, ask for clarification. Because we want to make sure for this one, this was the radius. So double this is the diameter, that's 12. 12 squared plus x squared is 25 squared. And then I solve for x. It's tangent, I set them equal to each other, I solve, we're good to go. Yeah,
I still don't really know how you got R up at the top one.
how I got R up here?
Yes.
Okay, do you see the radius to the tangent line?
Yes.
So now I have a right triangle.
Yes.
Do you see I have one side that's A?
Yes.
And another side that's B.
Yes.
So I have A squared plus B squared is equal to. Now this C is my hypotenuse, it's the side opposite my right angle. So this C is going to have a length of R plus 4.
Yeah, now I see it kind of.
Okay? So there's my R plus 4. And now what I'm going to do when I square it, I need to make sure, and sometimes it's easier to write this as R plus 4 times R plus 4, because then you can see your first terms, your outside terms, your inside terms, and your last terms. And then I'm like nervous. You're like, oh no, quadratic. Don't worry, it cancels out. Okay? Are we good? To pick your seat at the movies. Now I know this is dark, so I'll put some pens out there to tell you. You can pick pink seat. You can pick orange seat. You can pick blue seat. You can pick green seat. And you can pick purple seat. And of course it goes without saying that you want to pick the best seat. So last night my husband and I, oh no, that's crooked, that's gonna drive me crazy. Last night my husband and I went to a concert and it was general admission, but it was seated. Freaked me out. Because instead of having like general admission where you stand and you watch, and you can mill around and change your view, and somebody big sits in front of you, stands in front of you, it's okay, you just move, right? General admission concerts. But it was seats, and I was like, I gotta pick the best seat, because we got there early enough to have a lot of choice. So I'm like, do I want to be on this side? And I'm walking around, I want to be on this side, because I want to make sure I have the best view. And then it hit me. I'm teaching this in geometry the very next day. So I knew exactly where to sit, and I had a great view. My husband looks at me and he goes, I'm not sure I want to pick these seats, but we can see great. I'm like, I know! Because I'm a geometry teacher. Which is the best seat? Try to talk to your partner. Go. Most pinks, some oranges and greens, and no blues and purples. You want to know what the answer is?
Purple.
Green, orange.
They're all great seats.
What?
They all have the same view. They all have the same view angle to the screen. Your movie screen, I want you to think of it as a diameter. And I want you to think of the angle created with the vertex on the circle. And that angle is created from two chords that share that vertex and the endpoints. Every single one of these seats has the same angle. I'll show you how. First, a little bit of vocabulary. An inscribed angle, an angle in the interior of a circle whose vertex is on the circle and two chords that share an endpoint. Your inscribed angle has endpoints on the circle, and this endpoint is shared by both the chords. The intercepted arc is the arc on the circle defined by the endpoints of the chords. So those endpoints on the chords define your arc on the circle. An inscribed polygon is a polygon with all vertices on a circle. A circumscribed polygon or circumscribed circle is a circle that passes through all the vertices. We'll get to these in a little bit. First, we have an inscribed angle. If I have a central angle and that's x degrees. True or false, its related arc shares the same degree measure. True. Thank you. You made me nervous for a little bit. Those two things, this angle, this arc, same measure. Now I want you to imagine pulling this angle way back here. Do you think it's going to be smaller, bigger, or the same size?
Smaller, one half smaller.
What do you think? I heard smaller, 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 one half smaller. All right, I'm going to show you an angle. Do you see my, maybe I'll do it this way. Do you see my finger here holding this angle? What happens when I stretch it way back? Does it get smaller? Bigger here? Smaller? It is half.
What did I say?
It is half. If you have an inscribed angle, its measure is half the measure of the arc and the central angle.
Whoa.
And the central angle. All right, hey, we talk about these corollaries like, oh yeah, while we're here, let's go through one more thing. And it goes like this. If I have arc AB, which is its inscribed angle? ACB or ADB? Yep. So here's angle C, and here's angle D. Are you ready for this? If this is equal to x degrees, this one is 1/2 x degree, and so is this one, because they both have these points as the end points to the chords that create their angle. So this is the movie theater problem. Whether this vertex is up here on the circle or down here on the circle, anytime that this vertex is on the circle, the view, the angle is the same. Just in case you're curious, we sat here. Handsome likes to be on the aisle. But we had great seats. If you have an angle inscribed in a semicircle, and this is going to make total sense to you, are you ready? Here's our semicircle, right? What's the degree measure of a semicircle?
180 degrees.
What's the degree measure of a straight angle?
180.
Trick question. What is the measure of the inscribed angle?
90.
Every time. Because its chords intercept that semicircle. So this right angle, and again, get ready for the Pythagoras problems. Get ready for the Pythagorean theorem. A squared plus b squared is c squared. There's more right angles coming at us. Hey, this next one's kind of cool. Are you ready? Do you see here that angle E, its chords intersect at F and D, and its related arc goes around this part of the circle? You okay with that? All right. Do you see here that angle G has endpoints right here at F and D, and its related arc goes around the circle this way? Would you say that the measure of arc DEF plus the measure of arc FGD is the whole circle. Are you okay with that? So guess what? The measure of angle E plus the measure of angle G is going to be what? Half. So when you have a quadrilateral inscribed in a circle, opposite angles are always going to be supplementary because these two endpoints make up the entire circle. So these two angles have to be equal to half of their sum. So they're going to be supplementary always. So it's interesting whether I talk about the polygon inscribed or the circle circumscribed, it's the same picture. It's all about your perspective. Have you ever seen those drawings where it's like an old lady, or you look at it again, it's a young woman? Have you ever seen those things? It's kind of like this. Are we talking about the circle that's doing the circumscribing? Or are we talking about the polygon, the quadrilateral that's inscribed? All right, last one. Are you ready? If a tangent and a chord intersect at a point on the circle, then the measure of each angle formed is 1/2 the measure of its intercepted arc. Here we go. Ready? If I know that this is x, this is going to be 1/2 x degrees. If I know that this is y, this is going to be 1/2 y degrees. The measure of y plus the measure of x are going to be equal to 180 degrees because they're supplementary. The measure of x around the circle plus y around the circle is 360 degrees. So this angle is going to be half of that one. This angle is going to be half of that one. All right, here's what I want you to do. Turn it over, and you've got 15 minutes to lean in, to think, to work, to talk, to get some quality work in. Don't just get it done. Get it done well. Get it done right. So when we look at this first one, we have 140 degrees. Half of that is 70. We have 80 degrees. Double that is 160. The area around the circle is twice. The arc is half of the circle. Got it? All right. So let's take a look at this one here. In the diagram, it's given that the measure of angle y is 62 degrees. What is the intercepted arc? The definition of the intercepted arc is the arc that's formed by the endpoints of the angle. These chords that make up this angle have endpoints on the circle. So x and w are the endpoints of the intersected arc. So it's arc wx. What is the intercepted arc for angle xzw? It's the same one. So when we talk about the measure of angle z, that's also going to be 62 degrees. Now some of you went ahead and figured out the measure of arc wx. What would that be? Yeah, 124 degrees. And guess what you could do further on? You could then subtract that from 360 and get this arc around here. All right. It's a diameter, so it has 180 degree measures. When I have a circle, 180 degree arc, that means that this angle is going to be a 90 degree angle, so I can solve for x is 60. Here, this is twice this angle. Now, you've got to pay attention to that equal sign, because if you're going to say 4x is equal to 12x minus 100, they're not equal. 12x minus 100 is double 4x. It's twice as big. So if you want to make them equal, you got to double the little one. Double this is equal to that. This is half. So you got to double it. When you set up these two circles here, this angle is half of this arc. So you could half this, or you can double this one, it's your choice. Having this one might have been easier because they're both friendly numbers, divide by 2. In the diagram, WXYZ is inscribed inside circle P, so my opposite angles are supplementary. So I'm going to set each of them equal to 180 degrees. Their sums equal to 180 degrees and solve for X and Y. Take a look at this proof. We're going to talk about this next class. Given circle O, write a paragraph proof proving that these two circles are going to be, or those two triangles are going to be similar. Yeah.
For question 6, you said the whole interior angle measures are at 180, but
No, I said opposite angles
okay.
are supplementary.
Okay.
So we can finish doing that one. 180 minus 126. So 18y is equal to 54. So y is equal to 3. Here 18x is equal to 180 minus 72 divided by 18.
So,
X is equal to 6. Okay? All right, so you have a quiz on this next class. Can I just say the packing up when there's still 3-4 minutes left of class is rude? It creates noise and distraction. Next thing you know, I'm yelling. Nobody likes to be yelled at. So you have a quiz. Next class. Look carefully over the board here. Make sure that you know what we're talking about. SOL, make your packet, your corrections for your Unit 8 polygons test. Instead of doing a retake in this testing season, we figure you guys have enough tests to take. So instead of having you come in for the retake, quality corrections can earn half credit back. So if you got 10 wrong, you can earn 5 points back just by doing a good job on your corrections. I had people at my door today waiting to come and talk to me about corrections today. Come and ask me, it takes 10 minutes, 5 minutes in the morning. If you're like, I can't get this one, can you please explain it? Because I'm not giving you points on corrections that aren't correct. I can't hear you. Sure, opposite angles and you're packing up and I can't hear a person that's 8 feet from me. The opposite angles in a quadrilateral are going to be supplementary. So this plus this is this plus that. You think they should use the same variable?